move on to introduce our first invited speaker, it's a pleasure to have Yuping Luo with us. He is an assistant professor at the University of Hong Kong. He received his PhD degree in 2014 from the Chinese University of Hong Kong, supervised by professors Xiao Tang and Xiaogang Wang. He has published more than 80 peer-reviewed articles in top-tier conferences and journals, such as PAMI, IJCV, ICML, ICLR, NeurIPS, and CVPR, with more than 12,000 citations in Google Scholar. He has won a number of competitions and awards, such as the first runner-up in the 2014 ImageNet Challenge, first place in 2017 Davis Challenge on video object segmentation, gold medal in 2017 YouTube 8 million video classification challenge, first place in 2018 drivable area segmentation challenge for autonomous driving, PhD fellow award in 2011, Microsoft Research Fellow Award, and he was named one of the young innovators by the MIT Technology Review, Innovator under 35 for Asia Pacific. So yeah, it's our pleasure to have Yuping, and please feel free to take it away.
Okay, thank you for the introduction. Today's talk is about instant level visual perception and generation. Okay, this is about the outline of the talk. I will firstly introduce how to model instant object mask in the polar space instead of the original Cartesian space. Okay. In the second part of the talk, I will introduce a new benchmark for the full body human landmark detection task. And the first part, I will talk about the virtual fashion try-on task by using a preserving generating mask method. Okay, hopefully I can have, we can have a 5-minute Q&A section. Okay, this is the first part of the talk. To model the mask from the Cartesian space to the polar space, and this is the related work. So the task of this work is about instant segmentation, okay, which needs to segment every single object in a single image. And this task is different from image classification, which assign different labels to an image, for example, a person, shape, a dog in this example. And also it's different from object detection, which predict the bounding box of different objects in a single image. And this also different from semantic segmentation, which we assign a single label to each pixel in an image, but it does not distinguish different object instances. This is the motivation of modeling the mask, instant mask from in the polar space. Okay. For example, we have a foreground object, okay, represented in blue, and the background in green. Okay, if we represent the mask by in the original Cartesian space, the XY coordinates is hard to find a linear decision, single linear decision boundary to separate the foreground with the background. Okay, and if we switch to the polar space by modeling the object mask by using the angle and the radius, okay, and it's easier for us to find a single linear decision boundary to separate foreground and background. So at the right hand side, we show an example. For example, given an original image, okay, the conventional pixel-wise representation is it's like this, okay. Each pixel represented by a different label, okay. In this example, the foreground is in blue and the background in purple. And the figure in cat here shows the XY coordinate for the mask in the original Cartesian space, which represent by the XY coordinates. And in this work, we will represent the instant mask in the polar space by using the angle and the length of the rays at different angle. So here we compare two-stage method with a single-stage segmentation pipelines. And in this work, we want to we show that by using the polar space, we can reduce the complexity of two-stage segmentation pipeline. And for example, here is the state of the two-stage instant segmentation pipelines. The mask RCNN pipeline follow the detection and then segmentation strategy, which contains two stages. First stage is the ROI proposal, and the second stage is detect and segment in anchor box. Okay. And we further compare our methods in F here to many representative existing segmentation pipelines, okay, including the two-stage method from A to CAT here, okay. All of them have two stages. The first stage, as we mentioned, is ROI proposal, and the second stage, detect, followed by segmentation. And even the single stage method, like you get here in doc, it needs to predict the bounding box. It still relies on the bounding box information. And for the other single stage method, tensor mask, they represent the mask in 4D tensor and followed by a module of tensor alignment. So here we show that our system has the most simple pipeline and doesn't rely on the bounding box information for instant segmentation. Okay, this is the general pipeline of the PolarMask. PolarMask is the name of our system, which contains a backbone network and feature-driven network to extract features in multiple scopes. And also we define two heads. The first one is the same as the conventional classification head to predict the label of each instant mask. And the second one is the ray regression to predict the length of rays in different angle of the in the polar space. So that instant segmentation is recast in the polar space, which is to find a pixel. Okay, to find a pixel that is the center of the mask and also predict the length of rays from this center in the polar space. Okay, for example, for each pixel, we will predict whether this pixel is the center point. And from this center point, we'll predict length of the rays, okay, in different angle, okay. And then we will connect all these control points to form the instant mask. So that if we want to perform single stage segmentation in the polar space, we need to redefine the mask representation in the polar space. And also we need to redefine the centerness in polar space. And then we need to redefine the IOU representation in the polar space. Okay, first of all, this is how to represent the mask in the polar space. For example, we model instant segmentation by using the polar coordinates as k-rays, okay, from the center point with uniform angle distribution. Okay, this is example. This is the center point, and di here is the ray. So here we represent the mask by using a center point and the distance between the center points to the contour at different angles. Okay. Finally, we connect all these contour points to represent a mask, instant mask. So here we show that for each point on the mask contour, the position can be calculated like this simple equation. X and Y, X, I, Y, I here are the position of the mask contour. Okay, and SC and YC here is the position of the center point. Di is the length of each ray, and theta is the angle. Here show that we how we define the centerness in the polar space. Here we compare the centerness in the original Cartesian space for bounding box detection to the polar centerness we define in the polar space for instant segmentation. The centerness of in the Cartesian space is defined for box detection in FCOS presented in ICCV19. Okay, it basically divided by, for example, given a candidate center point here, the centerness is divided by the distance to this center point to the left bounding box boundary, okay, denoted by L here, and to the right right-hand side denoted by R, and also the distance from the center point to the top and the bottom boundary. So the centerness is divided by the ratio between all these distance. And here we define polar centerness in the polar space, which is represented by the minimum length of rays, okay, the minimum of D1 to Dn here, and divided by the maximum length of rays. For example, for this point, the polar centerness is smaller than this point is shown at the right hand side, okay, because the minimum length of the rays divided by maximum length of rays is smaller than the point at the right hand side. Okay, this is the definition of the IOU in the polar space. Basically, here we show the example of a PolarMask. The ground truth PolarMask is in green, and also this is ground truth PolarMask, and also the predicted PolarMask in orange. Basically, we want to find the overlapping region here as the definition of the IOU, mask IOU in the polar space. And turns out that we have this formulation, and which can be represented by a very simple form, which is just the minimum length of ray divided by the maximum length of rays, and then we sum up all this ratio in the entire polar space from 0 to 2 pi. And we also put a log here to turn the polar IOU definition into a loss function, okay? So that we use this polar IOU loss function to for the regression task of the rays in the polar space. Okay, here we summarize the network design of the PolarMask system. Okay, the PolarMask system contains the backbone network and the feature pyramid network to extract features of different levels. And we also define two heads, the classification head to the label of each mask, and also the ray regression, okay, to predict the length of rays. And the object mask is obtained by the center point and connecting all its rays. Okay, for example, starting from the center point, the point in the mask contour is determined by the distance and angle of the rays in the polar space. And since the angle is directional, so that it is quite easy, convenient to connect the points into an entire contour. And PolarMask can be viewed as a generalization of FCOS method for object detection, where the object centerness is defined in the Cartesian space. Okay, in other words, FCOS is a special case of the PolarMask system because the bounding box in object detection can be just viewed as a simple mask with only 4 rays at the bounding box 4 corners. Okay, this is the general paradigm of PolarMask we showed before. And here are the experimental results. We compare with the prior systems on the COCO test set in terms of different backbone networks and the training aprons. Okay, we compare with both two-stage methods and one-stage methods. For example, representation compared to the representative two-stage segmentation pipeline, masks are seen here with the same backbone network. Okay, and also the same training app. Okay, we see that PolarMask also has a large gap compared to two-stage method. However, if we added one deformable convolution layer and we train more apples, okay, we see that the performance actually on par with the two-stage algorithm. And the advantage of the PolarMask is a simple pipeline and the efficiency of a single stage method. And we also do ablation studies. For example, we evaluate the performance of different number of rays. For example, we find that in the COCO data set, when the number of rays are more than 36, and the performance on the COCO data set are exaggerated. And we also compare polar IOU loss function, okay, with the original smooth L1 loss for the regression task. And we see that the polar IOU loss function for ray length regression improve the original smooth L1 loss function. We also compare the polar centerness definition with the original centerness definition in the Cartesian space, okay, and see that in the PolarMask system, okay, the PolarMask system with polar centerness definition outperform the original centerness definition in in the Cartesian space for bounding box detection. And here we show that the PolarMask system can achieve good performance without using the bounding box information. Okay, here we compare a system, PolarMask system with or without the bounding box branch, and we see that the performance are comparable. Okay, for visualization, here we compare the object centerness using the Cartesian space and the polar space. The result of the original centerness are shown at the left-hand side, okay? And at the right-hand side, we show the polar centerness, and we see that actually polar centerness find a more meaningful center for all these examples. These are the visualization for more visualization for the segmentation results. And here we have a failure case, okay, when the object contours are complicated. Okay, the mask representation in the polar space is a bit challenging to model this complicated contour. We may need to use more number of rays, okay, to improve the accuracy of the mask representation for complicated contour. Okay, this is the second part. We will introduce a new benchmark for full body human landmark detection. The related works from these two papers presented in this ECCV this year. The original human landmark detection only detect the landmarks on the human body, okay, like this case. And in this benchmark, we want to predict all the landmarks on, including the landmarks on face, hands, feet, and torso, okay, simultaneously. Okay, the conventional pose estimation, okay, predicts the landmark points on human body only. And here we present a new benchmark to predict totally 133 dense landmarks, okay, with 68 on the face and 42 on hands and 23 on the body and feet. And actually, full body pose estimation is challenging as previous pipelines for human pose estimation job in this new benchmark. And here we evaluate the performance of the pose estimation methods. Okay, and here we propose a new method, SoonNet, to improve the performance on this new benchmark. And also, we see that the full body benchmark proposed in this work can be used to pre-train CNN for various downstream tasks such as face alignment and hand key point detection. Okay, as we show in figure cat and dog here for facial landmark detection and hand key point detection. We compare the performance of a CNN module for example, for facial landmark detection without pre-training on the new proposed human whole body benchmark. And we see that if a system is trained on the whole body benchmark, the error of face alignment can be reduced. Okay, this is about how to build a whole body benchmark. Okay, first of all, we annotate face, hand, and foot key points on the whole training and validation set of the COCO benchmark. And we combine these annotated labels with the original human body key points labels provided by the COCO dataset. So that we combine all these labels as our whole body annotation. That is for each person, we annotate 4 types of bounding box, person, face, left hand, and right hand. And eventually we have 133 key points for each person, and 70 for body, 6 for feet, and 68 for face region, and 42 for hands. This here at the right hand side we show the definition. For example, the definition of the landmark points on on the torso of human body, and this is 68 data points on a human face, and also the definition of the landmark points on hands and feet. Okay, and about the annotation methods, okay, the first step is for each individual person, we manually label the face box, left hand and right hand boxes. Okay, and then we will perform quality control. Okay, the annotation of this bounding box is checked by the other group of annotators. And for the first step, for each face and hand bounding box, we will use a pre-trained face hand key point detectors to produce pseudo labels. Okay, this is a semi-automatic method in order to speed up the annotation process because we estimate if we manually label all the key points in the bounding box, okay, the cost for professional annotator is up to 10 minutes per face region and 1.5 minutes per hand region and 10 seconds per bounding box. So that is very expensive to manually label all the landmark points. And finally, we will perform a manual correction of the wrong labels and further perform a quality control. Okay, for example, we show that about 28% of the hand key points and 6% of the face key points are labeled as occlusion. Okay, and we will manually correct these labels. We ask the human annotators to manually correct these wrong labels. And by using these semi-automatic methods, we reduce about 89% time required for data labeling. Okay, this is at the right hand side here, we show the number of annotation. For example, there are for the entire COCO body data set, okay, there were around 4 million key points on face, okay, and 2.5 million on body, right? And here we compare the COCO whole body benchmark, okay, this new benchmark is called the COCO whole body benchmark with many existing representative data sets in terms of the number of image, number of key points and bounding box, and also the number of instances. Okay, we compare with many existing data sets. This is for human body, and the second part is for hand key point detection, and the last part is for face. And we see that the number of images is the same as the COCO because we label all the images from COCO. And for the COCO whole body data set, we have the largest number of key points, which is 133. And we label all different bounding box on the whole human body and the key points on the whole human body, including the body, torso, hand, and face. And also the number of instances, which is also the same as the original COCO dataset, okay, because we label each person from the COCO dataset. Okay, this is the diagram, the network diagram of SoonNet we propose for this new benchmark, which basically contains the feature net and FPN to extract features, and a similar architecture as the HRNet to fuse the features from different scales. Okay, we call it body net. And also we design the face head and hand head to predict the landmarks on the human face and hands at a small scale. And we retrain many existing human pose estimation method on this new COCO whole body dataset. And we compare the performance on different human body region, okay? And we see that the performance of SoonNet was better and outperformed the existing works. Okay, this is the first part of this talk, which is about virtual affection try-on by preserving and generating mask. So this talk is given a closing image. Okay, we want to change the close of the present image. Okay, and the task is to preserve the pattern of the this closing image, and also to preserve the body pose. For example, the detail of hands and also the detail of the hair, okay, in the person image. And in this task, the person image are typically partitioned into different difficulty levels, okay, by you according to the human pose. Okay, for example, this is the EC case with frontal pose. And here we show the normal difficulty level with a little bit pose change. And this is hard cases because the human hands and human pose has occlusion with the curves image. Okay, this is a harder case because the human has large pose. Here we show that we assign random the same curves image to random person. Okay, this is demo showing the robustness of our systems to assign a random curves image to a random person image. Okay. Actually, visual try-on, the task of visual try-on is very challenging. Here we show the previous result from the written paper and the CP written paper. And here we want to change the assign the target curves to the reference person image. And we see that from the written result, the pattern of the curves image cannot be preserved, and also the lower body curves and the details of the hands cannot be preserved. And similar effect produced by the CP written result, we see that, that the result has many artifacts, and also the pattern of the curves image cannot be preserved. Okay, we compare more result with existing work with the result from CP written. Okay, ACGPN is our method. Okay, and here is a result from our full model, okay, combining all the different components together. And ACGPN asterisk is the result, but we remove a module, okay. Okay, this one, ACGPN vanilla is the result of our system, but we remove an important module. And we compare the curves image with different difficulty level, okay, for example, from EC, medium to hard. And the first step is to, given the person image, we need to perform human parsing, okay, I show in the segmentation results here. And we want to assign the target curves image to the person image. We also zoom in the important region, okay, we want to highlight to compare different results, okay, by 2.5 times. As we can see, our system, ACGPN, compared to our system, but without an important module, okay. This module is to constrain the deformation of the curves image. And so that if we found this important module, the curves image after try-on, we have this unreasonable deformation, okay. And here at the second row here, we compare our full model with the result from CP written, and we highlight the region of a human hand. We see that our system can preserve the detail of the human hand, but the existing work cannot. At the third row, we also highlight the region of human hand, and we also see that our full model can preserve the details of human hand very well. Okay, this is a diagram of the our system, ACGPN, and this is the inference step. Okay, the overall inference step contains 4 different substeps from step, okay. And the step 1 is to predict the mask of the Crookes image after try on. Okay, for example, given the image as input, we will produce segmentation passing result like this. And then we will remove the label of human hands and combine with the target clothes. We want to change the clothes of the person image. Okay, we want to predict the region of hands after try on. Because in this example, we want to change the long sleeve clothes to a short sleeve t-shirt, so that the region of the human hands must be changed. Okay. And for the second step, given the region of the new region of the human hands, we predict the clothes region. Okay, this is from a long sleeve clothes to a short sleeve t-shirt. This is the segmentation mark of the short sleeve t-shirt. And we perform the clothes swapping by combining the mask of this t-shirt with the target clothes image here. And this is a warp result. We introduce a new second order difference constraint to warp the clothes. Basically, this constraint is saying that we need to preserve the distance between different pixels in the clothes image after try on. For example, we compare the result without this second order constraint, and we see that in this column, okay, the distance of different pixels of the original clothes image cannot be preserved. And also with this second order constraint, okay, we can preserve the distance between the pixels in the clothes image. So we produce a smooth try-on result. Okay, this is the first step of our system in inference. After we predict the mask of clothes and also the new region for the human hands, and we want to produce the region we want to preserve. For example, here we want to preserve the original hand region here, and also the hair and human face, because we want to directly paste this region to the target image. We don't want to regenerate this region. And the final step, we combine all these results to generate the final try-on result. And this is the training methods. I may skip the details of this slides. Here we show that how we define different difficulty levels for the task of fashion try-on. Okay, basically we compute the center point of the human pose, and then we average the distance of different key points on the human body to this compared to this center point. If a person image has large pose, and this distance may be small. Here we show more results for the try-on experiments. Okay, compare with free existing work, written and CP written and VTNFP here, and we compare our full model ACGPN with the free existing works. And in the first row here, we highlight the regions of lower body clothes because we just want to change the upper body clothes, but we need to preserve the region of the lower body clothes. And we see that the result from all existing work, the lower body clothes also change because the entire region is generated by the GAN model. And the second example in the first row, I show at the right-hand side here. Okay, we see that this reference person image, the lower body curves has a pattern here. Okay, and our full model can preserve this pattern very well. In the second row here, we show that whether different algorithms can preserve the pattern on the target curves. In these two examples, we show that our result full model can preserve the letters W, E, and C here. Okay, but Async works cannot preserve these letters. And the second example is that we show our full model can preserve the logo and also the letter of Puma here. And in the third row here, we show that this is example to change the long sleeve shirt to a t-shirt, a short sleeve t-shirt, so that we need to generate a region of the hand. And we see that the full model of our systems can generate a reasonable hand region, but the existing works cannot. And the example of at the right hand side here also, we show that we can preserve the hand regions, okay? Even this hand region has a occlusion with the close image. At the bottom here, we show the more complicated results, okay, which the human pose has a larger occlusion with the close image. Okay, this is more result compare our system with existing work, okay, and we see that we can preserve the pattern of the close image as well as the detail of the human hand here. And we also present the quantitative results on the data set compared to existing work in terms of the SSIM matrix and also the IS score. Okay, this is the conclusion of these talks. The first one is modeling mask in the polar space may reduce the computational complexity of instance segmentation, but slightly sacrifice mask accuracy for the object with non-rigid and complicated boundaries. Okay, so that more effective shape modeling methods could be explored in the future. The second point is that the jointly estimating landmarks on the entire human body, face, hand, and feet could be helpful in downstream tasks such as facial image understanding and face alignment, and also hand key point prediction. And the third is that for fashion virtual try-on, it's important to preserve the details of the human pose, like face, hands, and feet, as well as to preserve the details of the curving image, such as the patterns and logos and the letters on the target curves image. Okay. And we will also consider more constraint of the human body and the curves, for example, preserve the cutting of the curves image in as the next step. And we release the curves of all these projects here. Okay. Okay, this is the end of the talk.
Thank you. Thank you, Ping. So a virtual clap, since we cannot do a physical live one. Yeah, very interesting talk. We already have some questions coming. So let me read to you some of these questions. And I think these were questions that were asked during the talk. So some of them refer to the first part, some of them refer to second and third parts. So let me start with the first one. This is the first question, which I think you can also read, Ping, by the way, if you click on Q&A, the Q&A feature in the Zoom application. So the first question is about instance segmentation. It mentions, it may be a question directly related to PolarMask, is asking if the instance segmentation stage makes it very slow by computing the lengths of all the rays from center to extreme.
This is actually efficient than existing two-stage pipeline. Okay, because we only use 36 rays, and also we did not need to rely on the bounding box detection.
Got it. Thanks. So I will mark that question as answered. And we'll have quite some time for questions. So for the attendees, feel free to add more questions as we go here. So the second question from the person is asking if is it correct that ray regression is the line segment from center of mask to periphery in one direction?
Yes, I think the answer is yes.
Okay. And then the third question we have there is detections with PolarMask, sorry, trace a close contour compared to rectangular bounding boxes. This eliminated 30 pixels from the scene as part of detection. Have tests been done to check if this translated to better recognition?
Been done to check if this translates to better recognition. Is this asking about whether the PolarMask representation can help improve the classification branch?
Yeah, I guess the person who asked the question may add a message in chat if they want to clarify. So we can have, that person just added a new question, as you may can see there. There are fewer unwanted pixels, so is classification recognition improved in that case?
Actually, when if we improve the number of rays, we may improve the classification branch a little bit. Yes.
Great, cool. Yeah, again, feel free to tell the attendees, feel free to add more questions. And to the workshop organizers, feel free, if you want to ask a question, to unmute yourself and ask the question directly. I have a question for you, Ping. So in the talk, you're focusing on these different applications of segmentation and virtual try-on and landmark estimation, which are applications where, to some extent, for example, the specific details, for example, if we're talking about a person and we want to estimate the landmarks of a person, the specific details about that specific person, for example, are kind of lost. We want to generalize across different persons to detect the same key points. While one of the other topics we're interested in this workshop is about identifying and recognizing that person specifically. So have you ever considered a system to kind of do both, have these features that would generalize and detect landmarks across any person, but at the same time have other types of features that may help the identification of the person, the instance level recognition of the person?
So I am sure you are asking whether the learned representation can generalize to recognize a specific person, like with ID.
Yeah, so I mean that's one possible question. So I think you can take the question this way, but is there a way also to, for example, augment the systems or in such a way that they can both, for example, segment and identify the person, or both detect the landmarks, meaning the key points in the body, and also recognize, given that
yes,
maybe these are a little bit conflicting.
In the system of virtual try-on, we actually combine the representation of a human passing, that is segmentation, and also the landmark of a human body. And so that we also try to recognize we also have a project to recognize a specific pair of clothes image, so that this is similar to read identification of human body. Actually it's the read identification of human clothes of the human bodies. Yes.
Right. So my question was along that direction. For re-identification or identification, we want to keep features that are specific to that person, while for key point estimation or landmark estimation, we may want to abstract them away because we want to detect key points across many different persons, right? So yeah.
Yes.
I had a quick question about virtual try-on. So did you ever consider the texture and, for example, the reflectance of the closest when you're trying to change this closest between each other? Let's say this, if you have like a pretty shining closest, if you change that, does this like the reflectance, something still persist?
We just do the image warping at this stage. The closed textures is not processed by, for example, a GAN model. But in the future, at the next stage, we want to, for example, the texture editing for the after the try on, yes, and try to, for example, change the texture and of the closed image.